In today's video, we're going to look at the rate of change. Now, what does that mean? Well, I have two graphs here. The one is a straight line and the one is a parabola. And obviously, on first glance, you can see, well, there's a big difference. This one is straight and this one is bending. This one starts at the bottom, goes all the way to the top. This one kind of goes from the top and then goes back to the top. So the big fundamental difference between these things is this one has something that's constant, and this one has, well, something that changes. And what is constant here is the gradient. So when you did straight lines, you would have done the change in y over the change in x. This is the gradient, and you would have done maybe a little bouncing method, 1 2 3 hops, and 1 2 3, and this change in the y direction over the change in the x direction is what gives you the gradient. And with straight lines, it's the same at this place, at that place, at that place, at that place, everywhere, all the way up and all the way down. This gradient, this rate of change, how much y is changing with respect to x. So if x is getting bigger, then y is getting bigger in a certain way. This changes, well, it doesn't change. This change is constant. Whereas with a curved line, there's different rates of change. If I go to look at this line over here and the line over there, it's very simple or quick to see that, well, let's just start off with a simple basic thing. If I wanted to find the rate of change here, and I zoom in and zoom in, eventually if I zoom in, well, let's say at that point, obviously it's a curve, right? So it would curve, but if I zoom far enough in, eventually, this is my little example of having a little magnifying glass there. If I zoom in far enough, I'm going to have a straight line. And on this side, if I zoom in here and I, go in, then I'm going to have a straight line. And to find, well, if you zoom in far enough, it's going to look like a straight line. But obviously, if you zoom out again, you're going to see it's a curve. So what we can do is we can find the rate of change of this straight line by looking at how much y is changing when x is changing, doing a little triangle there, or how much y is changing here. So for example, if I zoom that out, I can measure this distance in y and that distance in x for this line, and for this line I can see the same thing. And just with these two lines on the outskirts here, I can already see there's one big difference. This is a positive gradient. It's going up. You would want if I drew a graph and it's going up like this, you'd be happy if your marks went up, whereas this graph is kind of going down. So this is a negative gradient. So the rate of change here on this side of the graph is actually positive. It's like if x is going bigger, then this is going to go higher. Whereas in this one, if x is like changing, then y is getting smaller. So there's a big difference between here and here. But if I went all the way down here, then, and I drew a line there, it would probably be like, if it's exactly at the turning point, it's going to be a flat line. And then I'll see, okay, well, there's no, like the gradient here is nothing. It's like 0. It's a flat line. There's no incline. So everywhere across this curve, as I move, the rate at which things are changing is not constant. And therefore, it makes this curve. That's actually why we see the curve, is because the rate of change is different. Now, you might ask, why do we want the rate of change? And to be honest, for your IG exam, you just want to find the rate of change because you want to get the marks in that question. Later on, you'll see like reasons for why people want to find the rate of change, especially when we look at kinematic graphs, like cars speeding up and speeding down and how quick and power, like how much power they have, etc. But I don't want to go into the detail of that today. I just want to kind of bring the point across that we have a gradient here that's constant, and here we have a gradient that's forever changing. And here it's easy to find the gradient and we can calculate it perfectly. But here we don't know the math yet. Maybe you do, but we need special math to actually find the rate of change at this point. So we're going to first of all see how we do it manually. Now, I kind of already showed how we'll do it manually, but I have a past paper, let's say, question here that I'm going to quickly just rub this off and have that here. So this is a typical example of what they can ask you. Actually, two questions. And they say the diagram shows the graph of a function. So there's a little function, little curved line there. And they say by drawing a suitable tangent, find the estimate of the gradient of the function at point P. Now that's point P, and we want to find the gradient. And they say the estimate for the gradient because we can't graphically, because this is what they're asking, by drawing a suitable tangent. So by drawing a tangent, we can make a line, and it's easy to work out the gradient of a line. So let me see if I can do that. It's not going to be great because I'm going to use a marker, but this is kind of something that you should be able to do. I'm just going to see, let me just get this over here. So what I want to do is I want to get, the idea is, if the sketch is like this, I want to get my ruler. Okay, well, I had one job and I missed it, but the idea is to to get it at that point, that kind of the amount of deviation, or this distance and that distance, is kind of the same. I don't want a line like this because then that would rather give me the gradient at that point. But I want to draw a tangent at that point P. So if I do it really well, might get really lucky. And you can see that you have to work very accurately, but you can see kind of from that point, it's, there's a little distance that it seems like it's on the line, and that's kind of equal on both sides. And then once it may be at that distance, it goes away again, and that distance goes away. So now I've drawn the line. Now this tangent line, this is a straight line, and I can work out the gradient of this line just by seeing what the changes in y and x. Now, I don't necessarily have to use the very big triangle, but bigger triangles would give me more accurate results. In this case, I can, if I wanted the gradient, it would be the change in y over the change in x. Very important, this is graphically, and that's going to be an estimate. So if I'm going from this point to that point, I'm going positive in a positive direction. So the change in x is positive, and that's going to be 2.5. And from here going to there, let me just do that a little bit color coded. So if I drew a triangle, freehand triangle, that's the 2.5. Let's make that 2.5, and we'll use a different color for the change in y. And then I go up, and that's also positive. And I'm going to have to, I have very thick markers here. So I'm just going to go with, that's 3.3, I think. 3.3. So from 0 to 3, and you can see it's a little bit, the 3.5 would have been around there. So it's kind of almost there. And then I'll get my trusty calculator, and I'll say 3.3 divided by 2.5, and that would give me 1.32. And that would be 1.32. So the gradient at point P, estimated gradient is 1.32. And I'll just quickly do this example. I'm not going to work it out, but just kind of show you how I would draw the line again. I would try and get it as exact as possible. Something like that looks like a good idea. So I can see that this distance here and here, it's gradually going. So that tangent would give me, it's actually a nice number. That tangent would give me the gradient at that point, not anywhere else, but just at that point. One thing that I forgot to mention here is I don't have to use the very big triangle. I can use a smaller triangle. If I wanted to use this part over here and that part over there, that would have been fine. It doesn't necessarily have to be the biggest triangle. In this case, I'm going to use, let's say, the change in y. In this case, it's going to be -2 because I'm going down, and the change in x is +4. So the gradient for this line is going to be negative a half, or negative 0.5. And it does make sense because this line is going down. It has a negative gradient, and that one's going up and it has a positive gradient. So this is how you do it graphically. And by drawing a tangent line, you have to make sure that it touches, because in your exam, if it doesn't touch that line, if you miss it like I did here in my example, and you have the curve and you miss it, then they're not going to give you the mark. So you have to be very accurate and make sure that you get it as close as possible touching the line. And you can also not do this. You can't go over. So you have to work very, very carefully with these questions, and then draw your little triangle. Again, I made the big triangle here. If I wanted to use a smaller triangle like that, that would have worked as well. So let's say that just to prove it, negative 0.5. If I look at the distance from 1.5 to 1, that's 0.5, and I'm going down. And the distance here from 1 to 2 is actually 1. So it's the same thing. So it doesn't matter how big the triangle is when you do it. In the next video, we're going to look at how we do it when we calculate it. So for now, this was graphically, and it was an estimate. And when they say drawing a suitable tangent line, please draw the tangent line. Please don't go use the calculated method, because that's not what they're asking. So next video, we're going to look at the calculated method. Yeah, it's quite fun.